Okay, so welcome everyone to the first online plus offline hybrid colloquium. This is something that we are doing after a very long time. It's very good to have people here in person. There are, of course, a lot of people on Zoom as well. And it's a great pleasure to introduce Arka Banerjee. Arka did his undergrad from President's University, from St. Stephen's in Delhi. And he did his PhD from UIUC, working with Neil Dalal, followed by a postdoc stints as a TIPAC Fellow in Stanford, the Institute for Particle Astrophysics and Cosmology, and then a short stint at Fermilab as the Sham Fellow. And after that, he has joined ISER Pune very recently, just 3 months ago, as faculty. And Arka has worked on several topics in large-scale structure and cosmology, the interface of cosmological inference and nonlinear structure formation, and very interesting themes of research such as testing the nature of dark matter and what phenomenological imprints the nature of dark matter can leave on astrophysical observations by performing simulations of these effects, as well as on the statistical front, trying to extract more and more information from upcoming galaxy surveys, again using Nbody simulations, etc. as a tool. So several of these things we will touch upon in today's talk.
Thanks, Sasi. I take off my mask.
Yes, good.
Everyone 6 feet away. Okay. Thanks, Asim, for the invitation and this opportunity to talk about my research. So, as Asim nicely summarized, I'm going to touch on the themes of simulations and statistics and their role in doing cosmology with nonlinear structure formation. Right. So the last century has seen rapid progress in our understanding of the fundamental particles and the forces that shape physical phenomena around us. So we know the standard model of particle physics, we know GR, and why don't we apply this to the evolution of the universe as a whole? But while doing so, we've also come to know that our understanding of everything that's happening to the universe as a whole is not complete. In particular, astrophysical and cosmological observations have told us that the standard model of cosmology needs at least 2 additional ingredients, which are dark energy and dark matter. At this point, both are phenomenological in the sense that we know certain properties about them, but we don't quite know what they are. However, they also dominate the energy budget of the universe. So some of the most interesting questions in physics are to figure out what these things actually are, what their properties are, and so on. Now, in the study of cosmology, it is useful to separate the information into 2 components. One that comes from the expansion rate of the universe. And so when Hubble discovered the Hubble flow, or when you look at the supernova data telling us about the cosmic acceleration, those are statements about the expansion of the background. However, on this background, there is also the evolution of perturbations. So what I mean by that is, for example, how the universe evolves in terms of the perturbations that you see in the CMB, at the CMB epoch, to what you see today. So during the CMB, the fluctuations are pretty tiny around the mean. So they are roughly 1 part in 10 to the power 5. But once you look at the late time structure, the density contrast can be as high as 10 to the 4 if you smooth on small scales. So the evolution of the universe from the CMB epoch, when things were linear, fluctuations were tiny, all the way to today, is sensitive to all the energy components in the universe and their properties. So turning it around, if we understand this process well, it will allow us to say or refine our understanding of things like dark matter, dark energy, and so on. So let's talk about certain relevant length scales. So the universe is assumed to be homogeneous and isotropic on large scales. This is a representation of the SDSS data. So every black point that you see is supposed to be a galaxy that was measured by SDSS. And the idea is that if you consider large enough volumes, and you average this image over large enough volumes, then the density fluctuations that you get, or the fluctuations around the mean number, let's say, that you get, are quite small. This is true even at redshift 0, which is very important. Which means that for large scales, and by large scales I mean something above, say, 40 megaparsecs or so, you can describe the evolution of perturbations in the universe using perturbation theory. On the right are the equations for linear perturbation theory. They're quite easy to solve. And this actually provides a pretty good framework for analyzing large-scale structure data. So you can go down to 40 megaparsecs roughly, but you typically need higher order in perturbation theory to go down to those scales. And indeed, over the last couple of decades, these large scales have been well analyzed by multiple surveys. And a lot of information that we have learned about cosmology comes from this sort of an analysis. But we are getting quite close to exhausting all the information on large scales. Surveys like LSST or DESI, which will cover roughly half the sky, will actually get us really close to exhausting most of the large scale information. There are still things like primordial non-Gaussianity, etc., which we can still learn from on the large scales. But for most of the standard questions in cosmology, we are getting close to exhausting the information. So the next thing is to consider smaller scales. And by smaller scales, again, just to remind you, this is, say, roughly smaller than 40 megaparsecs or so. Now, why should we consider small scales? So the first motivation for doing so is to think about the number of independent regions that you have at a fixed smoothing scale. So you have one observable universe. If you think about smoothing on 1 gigaparsec scale, you can only fit so many such independent regions into your observable universe. On the other hand, if you smooth on small scales, you get a number of different independent realizations on those scales. So any statistical inference that you want to make, you have greater statistical power coming from the number of different realizations. So naively, the total information that you can have scales as k to k cube, where k is the wave number, which is roughly 1 over the smallest length scale that you can get. So a factor of 2 in scale, if you can go from 40 megaparsecs to 20 megaparsecs, in principle, you can unlock a factor of 8 in total information. Now, this is slightly optimistic because nonlinear evolution actually interferes with that calculation. But it's still a lamppost for you to sort of understand why you should go to small scale. The second thing is that these scales are already measured in surveys and often at the highest signal to noise ratio. The reason we cannot use them is because we are modeling limited, because we do not have the tools, or we do not yet have the tools, which allow us to robustly model these scales and then extract cosmological information from them. So what is the challenge? The challenge is that the density contrast is much greater than 1. So perturbation techniques are not applicable on these scales. And we are forced to use numerical techniques, which can be quite expensive. So that's the challenge. You cannot really use conventional methods that have been tested like perturbation theory on these scales. You need a completely new set of methods. But what's the promise? What can we get if we can analyze these small scales and extract information from them? So the first one is, this is something that appears in the science books of every collaboration.
Can I ask you, yes, what is the scale you mean by small scale?
That's a very good question. So I think the next frontier is getting down to, say, like 10 megaparsecs or so, which is the quasi-linear regime. You're still not inside virialized structures. But finally, we want to get even down into virialized structures, say a megaparsec or below, and robustly model the information there. Yes. Right. So what you get, if you can analyze the small scales correctly, you can test if dark energy is consistent with the cosmological constant at a significantly higher level of accuracy. You can test the effects of various dark matter models on structure formation. I'll briefly touch upon this later. The third one, which is actually pretty close to being realized, is to pin down the total mass of the standard model neutrinos. In fact, the current bound from cosmology is tantalizingly close to ruling out the inverted hierarchy of neutrino masses. So the inverted hierarchy is the one where you have two heavier mass eigenstates and one lighter mass eigenstate. So if you believe cosmological constraints, this one is close to being ruled out, and we'll definitely get there in the next 10 years. What I'm not going to talk about, but are equally relevant, are things like galaxy formation physics, substructure dynamics within halos, and so on, which have an equally rich phenomenology, but I won't talk about them and focus on the first 3 points. Right. So to model the small scales, we need to resort to numerical simulations. So the type of simulations that have sort of been the backbone of cosmology in the last 30 years or so are called Nbody simulations. And I'll roughly describe what they do. So since dark matter is the dominant clustering component of the universe, we consider the phase-space distribution of dark matter. So F is the phase-space distribution. So you can write down the equation of the evolution of that phase-space. And that coupled with Poisson's equation is called the Vlasov-Poisson set of equations, which is what you're looking to solve. Now, this is a 7D partial differential equation. What is typically done is to use the method of characteristics to convert the partial differential equations into a set of ODEs. The ODEs I've displayed here, and you can see that they look suspiciously like the equations of motion of particles moving under the influence of a gravitational potential phi. It is important to remember that these are not real particles. These are packets of phase space moving around. Okay? And these patches of phase space have the same mass throughout the simulation. And what is phi? Phi is the collective potential due to the presence of all such simulation particles under consideration. So that's the collective potential. Hence, you get the nomenclature Nbody simulation because you map the problem onto the problem of the evolution of n bodies under their mutual gravity. So this is what people these are the equations that people solve in simulation. And you can see that this way of solving the equations are inherently Lagrangian in nature, which means that wherever you have more particles, you have more resolution. So in that sense, this scheme is Lagrangian. And so what is typically done is to generate the initial conditions for these simulations at a time when perturbation theory is still valid. So as time goes on, these fluctuations grow. So if you go sufficiently back in time, you can use perturbation theory to set the initial conditions for these simulations. And then you allow the system to evolve under its own gravity. Now, if you have more particles in a given volume, it gives you a higher resolution. So you can resolve finer structures in the final snapshot if you have more particles. Now, naively, such a computation scales as n squared because you have to compute the forces on in a particular particle from every other particle and repeat the calculation for every particle. But techniques have been developed to allow for a much shallower scaling which goes as n log n using FFTs and trees and so on. But this is what an n-body simulation typically looks like. So this will loop. So once we go back to the beginning, you have a more or less uniform distribution of particles. They move under their own gravity to create what is known as the cosmic web, which is typified by these nodes, which are dark matter halos. These are virialized objects. You have long filaments connecting these halos. And you also have these really large empty regions called voids.
How sensitive are these final outcomes?
So initial conditions as set by the cosmological parameters, or do you mean the phases of what the actual realization was?
Like if you are distributing the particular kind of uniformity, then there is little bit of non-uniformity.
Exactly.
So how sensitive that non-uniformity, and non-uniformity should not be uniform. It doesn't that the inhomogeneity could be anisotropic or this, right?
So the inhomogeneity or the initial condition is, so this is just gravity acting on a set of n particles. So gravity is gravity, there is no scale to it, etc. So what is set down by the initial condition is what determines the final outcome in such a set. So the initial conditions are actually generated via perturbation theory. The lowest order one is called Zeldovich approximation. And they are generated so as to be consistent with a power spectrum at the time at which you are generating the initial condition. You want to be far enough back in time where questions about anisotropy, etc., are still things that you can compute within perturbation theory. So if your field is a completely Gaussian random field, so any statistics of it can be computed within perturbation theory. So you want to be far enough back that all of these questions are known from perturbation.
Okay. So my question is, suppose you know the initial statistics of the initial,
right?
And then finally you get something.
Right.
Now you know some other statistics on the final.
Right.
So how? So is it like a deterministic in the sense that of course the process is like a theoretic process, right? But suppose you use the same statistical characteristics of the initial condition, would the final statistic would significantly vary, or the statistically?
No, given a realization, the final state is typically the same. If it is not, then you have to refine your simulation, etc. On the other hand, what is typically done is you consider multiple realizations of the initial power spectrum.
Yeah.
And then you get multiple realizations of the final state. And I'll actually come to how you should compare these final states.
Basically, my question is multiple realizations are the same statistical feature, but the final results that you are getting, multiple results, you can still have the statistical data.
The statistics of the initial conditions are fixed.
Yeah.
The statistics of the final conditions are known.
Also fixed, yes.
And this does not play a role.
It is not here.
It is not here. Deep inside halos, you could argue that things start becoming chaotic. But at least on the scales that we'll talk about, say a megaparsec or higher, it is determined. Okay. So actually, for the last 30 years, we have sort of perfected these techniques. So for lambda CDM cosmology, where dark matter is completely cold and collisionless, and dark energy is just the cosmological constant, the Nbody method has been tested extensively and shown to produce accurate results. In fact, we can now run these simulations at multiple points in parameter space. So suppose we want to scan what happens as you change the amplitude of the initial power spectrum, what happens when you change the tilt of the primordial power spectrum, and so on. What happens when you change the Hubble constant, for example. You can now run simulations at multiple points in parameter space. And sort of see how things evolve. So, for example, the top left corner is when you really dial up the initial amplitude of the power spectrum, so you get a lot more clustering by Z of 0. Here you see examples where the amplitude was lower, and so you see less clustering. But now, what is happening is now, given the computational power we have access to, we can actually expand the range of theoretical models that we wish to test using nonlinear structure formation. But often, to do that, you have to update the numerical techniques that you use in these Nbody simulations. So next, I'll talk about a few examples that people have been working on. So the first one is massive neutrino cosmology. So we know that neutrinos have mass, or at least two of the eigenstates have mass. And their mass is high enough that even today, their energy density is non-negligible. So neutrinos were in thermal contact with the early universe plasma, but they decoupled while relativistic, which means even now their velocity dispersion is non-negligible. And also in terms of the number density, they are the most abundant particles after photons in the universe. The question is, how do we capture the effect of the neutrino mass in these nonlinear simulations? So the key difference from cold dark matter and neutrinos is how do you account for the thermal velocity? So if you try to naively extend the methods that were used in the cold dark matter case, where you didn't have a velocity distribution to draw from, that leads to additional noise from the fact that these neutrino particles keep moving around randomly. And the Nbody method is predicated on the fact that if you look at a particular region, the number of particles that you see there is a faithful representation of the underlying density. But if you have particles zooming around in the box, that is no longer true. And so instead of a nice cosmic web, if you run a simulation with neutrinos and really just randomly sample the velocity distribution, you get something that looks like this. That's just noise. So over the last 10 years or so, different people have come up with different methods to include neutrinos correctly in Nbody simulations. So I worked on two of these. So in the first one, what we showed was if you combine certain techniques of Nbody simulations with hydrodynamics, it is possible to beat down the noise that you get in Nbody simulations with neutrinos. There is actually an even simpler solution, which we showed in this paper, which says that if you think about the velocity distribution of the neutrinos, it's actually well known. It's a redshifting Fermi-Dirac distribution. And instead of sampling that Fermi-Dirac distribution randomly, if you sample it in a very precise fashion, where you actually just slice up the distribution equally, deterministically, you can reduce the noise in your simulation.
So can I, sorry, this is a naive question. What does noise mean and what is
noise basically means that, okay, so suppose this is what you were expecting as the final density field, where you see these features of halos, voids, filaments, etc. Instead, you see something like this. So this is the density field, which is basically counting up the number of particles, simulation particles, you get, say, per unit work. Right? Here, this is saying the particles are just almost completely uniformly distributed over the box. Right? And there are no apparent correlations. So you see reds and blues appearing right next to each other. So that's noise. As in, you're not really seeing the structures.
And this is a consequence of numerical resolution and things like that.
This is a consequence of the fact that neutrinos have thermal velocity. So if you want to model them and account for them in your simulation, you have to, allow them to move in random direction. If they do, they mess up the density. That was the original problem.
Oh, so you are planning?
Typically, it's called short noise. Huh? Yeah. Yes, correct. That's it. Yeah. Exactly. So how much noise you get depends on the velocity dispersion. So this is only the neutrinos. There's also cold dark matter. Neutrinos, if they form a non-negligible fraction, that reacts on the dark matter also changes that.
So what is the scale of this box?
This is 1 gigaparsec on each side. So the largest structure that you should see should be the biggest clusters, sort of. Yes.
Oh, so this, can I just understand as because you have given numerical bulk velocity particles which should actually have become heated in some.
That is correct. That is correct.
So it's an underlying conceptual mistake.
Right. Exactly. So the question is, how do you correct for this? So one way to correct for it is by combining what you just said, like hydrodynamics with Nbody technique. That's what we did in that paper.
But even in ancient days of Frank-wide simulations from cosmology. They got all the large-scale structure and showed that it didn't match observation. So what did they do and what are you not doing?
So back then, they were considering much more massive neutrinos. More massive neutrinos imply a lower thermal velocity. They were considering, I think, 40 electron volts and higher. And
are you saying that this neutrino said that the free-streaming scale is also gigaparsec?
Exactly. So I don't have a plot, but these neutrinos have exactly a gigaparsec.
Then we will not get any.
Yeah. But now with the current bounds, that is the range that you have to explore. Previously, the bounds were much weaker, so you could look at 40 eV and say that, large scale it matches, but small scale.
But here is neutrino on top of full document.
Right. It doesn't matter. He's only plotting neutrinos.
So it turns out that if you, instead of sampling the Fermi-Dirac distribution completely randomly or doing a Monte Carlo over it, if you do a deterministic sampling, you can beat down the noise to a great extent. So these two simulations actually have the same number of neutrino particles. The only difference is the distribution was sampled deterministically here, and here it was sampled in a Monte Carlo. The rest of the simulation ran exactly the same way. But here you can clearly see the structure that you were looking for. To cut a long story short, we now know how to run simulations with neutrino masses at the level that you expect. But in learning these techniques, we can now extend beyond neutrinos. So you can consider additional light species. And these light species, then you can consider what happens when they have a thermal velocity distribution, what happens when they have non-thermal velocity dispersion, and ask what is the characteristic signatures that I expect on structure formation. So in a paper that we put out recently, for example, we looked at signatures of non-thermal massive relics on structure formation and showed that even models that are allowed by Planck through the n-effective bounds can be ruled out by large-scale structure measurements like weak lensing around clusters pretty easily. So the darkest gray error bar is the error bar expected from LSST. And these models that were put forward by the last three authors give you predictions which are these flat lines. So that is still allowed by Planck.
What are you plotting?
So I'm plotting the difference from a lambda CDM universe, the residual between this cosmology and the lambda CDM cosmology. And the error bars, those are scaled to be relative error bars, is the error bar that I expect when LSST data comes through and we make these measurements. So this is measuring the weak lensing around massive clusters. So that's delta sigma over. Next, you can also see what happens when you change the properties of dark matter. So the search for microphysical constituents of dark matter or even a full dark sector is one of the most exciting problems in physics. There are certain models for which terrestrial experiments are best suited, but there are certain models of dark matter for which you can only see its properties through indirect methods. And one such model is if dark matter does not have strong interactions with the standard model, but has strong interactions with other dark matter particles. So this is typically called in our community a self-interacting dark matter. And these interactions would become important in regions where the density and the relative velocity of dark matter is high. And where is it high? It's high inside virialized regions like halos. Now, to model these sorts of dark matter, you have to adapt the numerical technique, because now not only are different dark matter particles in your simulations interacting through gravity, you also have to simulate what happens when two of them come and collide, right? And so once you take that into account, you get a number of really fascinating phenomenology associated with it. One is, for example, in CDM, the halos are famously triaxial. What happens in the presence of self-interactions, as you can guess probably, is that the center becomes rounded, right? Because different directions can now talk to each there are other predictions. In this paper that we put out in 2019, along with Sulu's actually, we showed once, so you'll see that this is again, so this is one of my favorite observables. This is weak lensing around clusters. And you'll see that in the presence of interaction cross-section, this profile changes. Again, the dark shaded regions are the error bars that you expect here from actually the dark energy survey. So this is current data. And it says that if you measure the weak lensing profiles around massive clusters, you can start ruling out cross-sections of roughly 2 centimeters square per gram. And 2 centimeters square per gram is exactly the constraint that you get by analyzing the bullet cluster. Now, as the experimental error bars get better, you'll be able to constrain these cross-section at an even lower level. But all of this, again, is possible because of these simulations.
But even,
yes.
even the density profile around a single cluster from the simulation has a large scatter from halo to halo.
That's right. So I should clarify. This is actually the stacked weak lensing profile.
Oh, okay.
So you take how many were these? 20,000 roughly. So and then you can match it to measurements, and you get very nice understanding. So there are other classes of dark matter models which are becoming popular.
Before you move on to the next one, the lot that we showed 2 slides before, spectralization. So similar things happen because of galaxy formation as well.
That's right. So one of the major degeneracies between SIDM and one of the major degeneracies of SIDM is baryonic physics, which is what motivated us to look at what happens on the outskirts. So these are clusters. So the effect of SIDM is visible out, say, like 400, 500 kiloparsecs. There you expect the effects of baryons to be somewhat lower than right at the center, where the coding happens. This was actually one of the reasons. You're completely right.
So this mainly comes from the fact that interaction changes the geometry or density distribution.
So what happens is if you core it, then the extra mass has to go somewhere. And all that it's doing is it's redistributing the mass. And weak lensing, because it's sensitive to the mass distribution, is sticking it out till some pretty far out radius.
In that case, the interaction with baryons will be also different, right? Because you are changing, in some sense, underlying dark matter potential. But
so
I don't know what is the amplitude of it. It's like 10% or what? I don't know. We cannot take it from here. It shows the potential here. Right?
So this has actually also been seen in SIDM simulations with baryons, this particular shape. It is correct that the overall offset was somewhat different. So yes, there will be a back reaction which you have to account for. Yes, so there are other classes of dark matter models called fuzzy dark matter, for example, which have become popular ever since the WIMP parameter space has been shrinking. So that says dark matter is made up of ultralight axion-like particles. And now because they're so light, considering particles or thinking about particles is not the right way to go about it. You rather think about the field as a whole. And so numerically what this means is instead of solving the Vlasov-Poisson set of equations, you solve the Schrodinger-Poisson set of equations. And this also has a fascinating set of phenomenology associated with it. You see in the simulation solitonic force forming at the centers of halos rather than the cusp that is predicted by CDM. You get the presence of interference fringes depending on what the mass of the fuzzy dark matter particle is, and so on. And this has been popular in the last few years, so people have come up with better and better techniques to run these simulations. And we have recently been looking at the effect of self-interactions within these solitonic or within these fuzzy dark matter models, and the effect of the self-interactions on how quickly different things get unbound. So if you can place constraints on that, you can place constraints on possible fuzzy dark matter models. So I'm going a little quickly because I want to get to the next part. So to summarize the section on simulations, I just want to say that numerical simulations are essential to work out the precise predictions of theoretical models, which can then be compared to existing and future data. And access to greater computing power actually allows for the exploration of a wider range of theoretical models. And I would really stress on the fact that this is exploration, because even after you've run the simulations, you often do not know all the interesting phenomenology that resides within it. Multiple things have been discovered for SIDM models many years after the simulations were actually run, and someone thought, oh, maybe it also affects this. So I would really stress on that exploration part. Moving to the next question, it was something that was raised already. How do you actually compare data and theoretical models? So theoretical models now include simulations out. Since we do not know the exact initial conditions, we cannot do an object-by-object matching. So whatever answers we have to look for must be statistical in nature. So if you're given the spatial distribution of data, say the positions of galaxies, we somehow need to summarize this statistically, compare it to the same summary statistic from simulation. So the next question is, what summary statistic should we use? So in cosmology, most analysis has been done in terms of the two-point correlation function, or its Fourier transform, the power spectrum. So this is the definition of the two-point function. So suppose you have some overdensity at some point x. You ask, if I move some radius r away from it, what is the correlation between the overdensity at this point and every other point at radius r? Then you repeat this measurement for every point. So that's the two-point correlation. And then the power spectrum is its Fourier transform. So this is just summarizing what the power spectrum does as a function of time. Let's not get into that. But the important thing is that the power spectrum of the two-point correlation function is a complete statistical description of your field if what you're trying to describe is a true Gaussian random field. So if you think about the CMB, that is actually very, very close to being a perfect Gaussian random field. Therefore, for the CMB analysis, all you need to do is compute the CNs. But the two-point correlation function does not capture all the information when the density field that you're trying to describe becomes non-Gaussian. And it indeed becomes non-Gaussian and extremely nonlinear at late times. So the presence of these halos, voids, filaments, etc., they bring out the non-Gaussian character. Therefore, to make full use of the information on small scales, we need to explore statistics beyond the two-point function. So this is not something new. People have thought about it for many years. So the obvious generalization is to think about higher order endpoint correlation. So just like the two-point measurement, two-point correlation measurement tells you the correlation between fluctuations at two different points, the three-point correlation function tells you the correlations when you consider three different points. You can think about four-point correlation functions and so on. However, what happens is that to compute these higher order endpoint functions, you need more and more computational resources. So for example, if you can think about how these things scale. To compute the two-point function, the process scales as n log n. For the three-point function, it scales as n square log n. For the four-point function, it scales as n cube log n, and so on. So it becomes very difficult to continue this analysis. Another approach has been to consider the full probability distribution functions of density. So suppose you are given a density field, you choose a particular smoothing radius. So here, this is for 10 megaparsec. You smooth in spheres of 10 megaparsec radius and plot the histogram of the densities that you get. You see that at high redshift, at z equal to 3, it sort of resembles a Gaussian. But at redshift 0, it is highly non-Gaussian. So people have tried to incorporate the full PDF, or the PDF measured, say, at different locations, not locations, at different density thresholds, as directly the measure. There are some drawbacks. You need a separate computation for each radius. So if you want to consider 10 megaparsec, you need to smooth your map on 10 megaparsec first. Then suppose you want to do it at 20 megaparsec, you need a separate computation to do that, and so on. Also, bin definitions introduce a degree of subject. So I'm going to talk about a completely different statistic and walk you through the salient features of that. These are called KNearest neighbor distributions. So first I'll describe the measurement. So for the measurement, suppose we are looking to characterize the clustering of a set of points over a certain volume. So here I'm drawing an area, but generalize this to a volume. First, we cover that volume with a set of query points. So those are the light points that I've put up there. And then these darker points are the clustered set of data that I'm looking to characterize the clustering for. What we do is for each of the query points, we use a tree structure to efficiently find the distance to the first, second, and so on nearest neighbor data points. So from this query point, I ask what's the nearest neighbor data point? It's probably this point. Second nearest is that point, and so on. Next, we repeat the same procedure for every other query point. So now we have a list of query points, distances to first neighbor, distances to second neighbor, and so on. Now suppose we focus on the nearest neighbor. We sort the distances to get the empirical cumulative distribution function of distances. This is a very simple procedure. You can do it for every nearest neighbor. So consider the list of distances to first nearest neighbor sorted, distances to second nearest neighbor sorted, and so on. So you get each of these cumulative distribution functions. So the takeaways from this slide is that a single measurement was sufficient for me to calculate all of these distribution functions and at various radii. And the second one was, this is computationally extremely cheap. So this was done on 20 seconds on a single port, whereas if you try to compute the 3-point correlation function of the same data set, it would actually take you hours. So this is really cheap. So now that you have this measurement, what is it actually measuring and why should we consider it? So to see what it actually connects to, you have to make the connection that the cumulative distribution function at a certain radius, or the value of it, is the fraction of points for which the nearest neighbor lies within the radius r. You have to make the connection that this is also the same fraction of points for which, if you drew a sphere of radius r, you would get at least one data point. Okay. So that's why it's p greater than 0 contained within that volume V of radius r. You can then try to write down what the generating function of this p greater than some 0 distribution, p greater than 0 is. And what happens in the generating function is that you see all orders of endpoint connected correlation functions appearing. So this simple measurement is actually capturing information about all orders of correlation functions. And the second nice point is that each different k, so if I measure the nearest neighbor distribution versus the second nearest neighbor distribution, what appears in these expressions are different combinations of all the endpoint functions. So if I measure multiple k nearest neighbor distributions, I am sensitive to different combinations of all higher order endpoint functions, which allow me to break various degeneracies. You can also write the KNNs, the CDFs as different 1-point averages. I won't go into that.
This is the same as what Simon White in 78.
That's
or is it beyond?
It is beyond. So if you think about what Simon White did in 1978, that was the void probability function. It is actually just this first one. It's, if you remove the 1, it's exactly the void probability function.
Right, but I thought he wrote down the expressions for all the.
No, he wrote down the expression for a different hierarchy, not this. This, so actually you can think of the k-nearest neighbor way of measuring things as the easiest way to compute the void probability function. It's the quickest way. But the second thing is that it also allows you to create this hierarchy of higher nearest neighbors. And that allows you to break degeneracies that the VPF by itself cannot break.
But can you compute it for any theory from scratch?
That's where the simulations come in.
Ah.
So what we have now is the fact that we can actually compute all of this. What helps is,
but what you will compute is the left-hand side.
what you compute is the left-hand side. So the left-hand side is a nice summary statistic. It is sensitive. You can show that it's formally sensitive to all of this. You can also compute it using the fact that it connects to one-point average, but different one-point average, which is also quite easy to compute from simulation.
What is this? Delta R is.
So if you take some radius r and you smooth your density field, this is saying that the CDX can also be written as expectation values over functions of this delta. Except what appears is exponential minus n bar, which is the mean number of objects that you're looking at, and so on. But the point is that all of these are connected. So the one-point averages are connected to all the endpoint functions. And what we are claiming is that a nice summary of them is that nearest neighbor distribution. And so as I was saying,
yeah. If you take your original map and you randomize the phases, someday, so you will make a difference between students.
Right, exactly, yeah. So the two-point function is not sensitive to the phases, but these will be sensitive. Right. So for cosmology, the integrals of the higher endpoint functions carry information, just like the two-point function carries information. So if you measure the KNN distribution, you are actually increasing the sensitivity to cosmological parameters. So physically, what is happening? A nice way to think about it is, if you have more clustered data points, and since the query points you are distributing uniformly over the full volume, if your data points are more clustered, there are more query points for which the nearest neighbor data point is farther away. So in terms of the CDF, the more clustered your data is, at a particular radius, you should find a lower value of the CDF. This is actually related to the void probability function. You just have to invert the thing. So what we did was we asked the question, if I show the same data to something that computes the two-point correlation function and to something that computes the nearest neighbor distribution, okay, how sensitive are each of these statistics to the underlying cosmological parameters? So this is done through something called the Fischer matrix analysis. So you change each of your cosmological parameters, you measure the two-point function, you measure the KNN distributions, you see how much they have changed compared to the noise in the measurement. And that actually tells you how sensitive these things are to various cosmological parameters. And so here I'm showing the corner plot. We'll see a lot of these in cosmology. But the idea is that the thinner your distribution is, this is supposed to be a posterior, the thinner it is, the more confidence you have or the more sensitivity you have to that particular cosmological parameter. And what we found is that irrespective of the cosmological parameter, using the nearest neighbor distribution allows you to get a really major gain over the two-point function.
So here you gone up to how many? Nearest one or nearest?
That's a very good question. This actually had 4 nearest neighbors. And you keep getting gains up to 4. Beyond 4, it seems to saturate. That is actually another good thing about this is you can keep increasing your data vector by adding another nearest neighbor and checking if you're actually gaining or not. And seeing where the information actually saturates. Okay, let me speed up a little bit, a view of time. But we also showed that you can compute cross correlations with nearest neighbor distribution. And so let me again walk you through what the measurement is. So once again, as we did previously, we first sample the volume densely with a set of query points. Now you have 2 types of data. So the green data.
Just one more question. One more question. The other thing is that how many query points you are going to choose. That is another free parameter to get.
That is another free parameter, and typically we found that if the query points are distributed with mean distances much smaller than the mean separation of your data points, then it doesn't, even if you increase by a factor of 8 or 10, that doesn't change.
Compared to number of particles in a simulation box, how many you have?
Oh, so not all. So we don't use all the particles in the simulation because we want to have the mean interparticle separation of the data to be comparable to what you expect for a galaxy sample.
So it's the halos.
With the halos, yeah.
Why does query points are random?
Yes, so you will see that my previous slide said random, but I changed it to query. It was because we started off with random, we realized that it doesn't really matter. You could place them on a grid, you will get the same answer. So that slide was holdover from my first time I presented. So you have two different types of data, so the green and the blue. And you're trying to ask whether there's a cross correlation between the clustering of the green and the clustering of the blue. Now what you do in terms of measurement is for each query point, you find the distance to the nearest data point of each data set. So for that query point, you find the nearest blue and the nearest green. Now you simply pick the larger of the two distances. Okay. Just pick the larger one. And then repeat that procedure for every query point. And sort the distances, get what we are calling the joint CDF. So that's the joint CDF. Again, it goes like a CDF, it goes from 0 to 1. Now, the nice thing is you can show that the generating function for this actually has all endpoint connected functions of type 1 and type 2. So suppose this is green and blue, then the generating function of that joint CDF has terms which look like green, green, blue, 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 green, blue, 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 green, green, green. So that's the 3-1. Then it has blue, blue, green, green, and all possible combinations and so on. So this way of calculating cross correlations is not only sensitive to the Gaussian cross correlation, which is the 2-point cross correlation, but all higher order cross correlations.
If I missed something, what was taking the larger?
So you see, if you take the larger of the two, that actually corresponds to the probability of finding greater than K1 particles of type 1 and K2 type particles of type 2. Otherwise, it would become an OR, which you might be able to work out, but the AND one was a simpler choice. Right, and so you can actually say when the two sets are completely uncorrelated, the joint CDF just becomes a product of the individual CDFs that we had talked about here. So I'll talk about one example that we showed where this is useful. So suppose you're trying to detect cross correlations for extremely sparse samples. So here, to give you an idea of sparse samples, we chose 1,000 halos from a 1 gigaparsec cube. Okay. Then we chose 1,000 other halos from a different box. So these are independent realizations. There shouldn't be any cross correlation. So we computed the 2-point cross correlation between those two. It should be 0, but because there is noise, you see this orange curves. So the 2-point cross correlation actually just oscillates around the true answer, which is 0. You can also cross correlate 1,000 objects in this box with 1,000 other objects in the same box. Okay. That's what you get for the purple line. So the purple line represents that measurement. Now you see the noise is so high in the measurement coming from the sparsity of the sample that the case where there is a true signal does not stand out from the case where there is no true underlying signal. Now we repeat the same measurement, but using the KNNs as a statistic. So you see that these tracks are the cases where there is no true underlying cross correlation. And then the purple dashed line is the case where there is a cross correlation. And it clearly stands out. Now this is cheating slightly because as you can see that the tracks are correlated. So you see that there's a large covariance in this measurement. So we tested it in a slightly different way. So we plotted the distribution of chi-square for the cases where there is no true underlying cross correlation, using the 2-point correlation and using the KNNs. In both cases, when there is no true clustering, they follow a chi-square distribution with the same number of degrees of freedom as the number of measurements. But the difference is, if you compute the chi-square of the case where there is a cross correlation using the 2-point function, it falls well within the null hypothesis. But if you use the KNN, this is well separated. So this takes into account the covariance matrix, etc. So this is a much more robust way of plotting this. But you see that if you use these nearest neighbor measurements for sparse samples, you might be able to detect a signal where the 2-point correlation function is unable to detect.
What was the definition of sparse in this example?
So this was 1,000 halos in a 1 gigaparsec cube box. So 10 to the minus 6 per megaparsec cube. So let me briefly talk about the first application to data. So we, in this paper that we put out a few months back and that got accepted last week, using these nearest neighbor measurements, we detected spatial clustering in just the 1,000 richest SDSS red mapper clusters. So again, this is distributed over a pretty large volume. And given the lack of time, I'll go over this briefly. So once again, we showed that if you distribute the same number of points, so 1,000 points, randomly over the red mapper, over the SDSS footprint, your chi-square distribution should look like these. If you use the 2-point correlation function, your chi-square measurement for the clustering is this. But if you use the KNNs, you get a much more statistically significant detection of the clustering of the sample. We were also able to show that this clustering is not consistent with a Gaussian field. This is not something that you do not expect it to be consistent with a Gaussian field because these are highly clustered objects. But it is still important to show that you measure this non-Gaussian. Okay. And we were actually able to measure that as well.
I guess the sharper way of highlighting this difference would be to ask how many red mapper clusters will you throw away before the 2-point function becomes consistent with norm.
That's right. We actually did this.
The KNN.
We did this. So it turns out to be around 500. Yeah. That's actually in the paper, but it's not the plot that we highlight.
So what is the significance of KNN detection at that point?
It's around 150 or 170 or something. Yeah. And even this 3 sigma maybe the 2-point function, I don't know. Let me skip this in the interest of time. But in another paper, we showed that to model these nearest neighbor distributions of tracers, you need, at least on quasi-linear scales, you need the same ingredients that people use to model the 2-point function on the same scale. So you do not need additional nuisance parameters to marginalize over to model these things. And you get really huge gains. So earlier I showed you the plot for matter distribution. Here we are actually showing the plot for the halo distribution. You get improvements by up to a factor of 3 if you jointly model the 2-point correlation function and the KNN distribution. So the point is that you need the same set of additional parameters to characterize both sets of statistics, but you get much more statistical power if you use the nearest neighbor distribution. And given that I'm running out of time, this is my summary slide for the nearest neighbor distribution. So there's a large amount of untapped information on small linear scales, which we are basically throwing away if we just consider the 2-point correlation function. The K-nearest neighbor is just one way of looking at that information, but it is actually quite fast and it has some really nice features. It is sensitive to all higher order endpoint functions. It is easy to talk about cross correlations using this nearest neighbor way of thinking. So this makes the KNN statistically powerful and much more sensitive to the underlying cosmological parameters than the 2-point correlation function. So there's a bunch of challenges ahead. So all of this has been shown on simulations. there's one very rudimentary application to data that I showed you. But if you really want to do cosmology, there are lots of things that we have to take into account. That's what we plan to do. So with that, I will stop and thank you for your attention.
Very interesting talk. Since many of you asked questions, I think it would be fair to give the Zoom audience a chance if somebody has questions. So people on Zoom can raise their Zoom hands if they have a question. And I will keep an eye on this, but if there are questions from there.
So I was about peculiar velocities, but anyway, you mentioned that is the one you will
look
into.
Yeah, so redshift space we haven't looked into yet. We are planning to do that. I was having an interesting conversation with Asim this morning. Yes.
Okay. So I was. You mentioned that if you change the mass of the dark matter particle or its other properties, that gets reflected in the structure formation, even at the lower scales below 40 megaparsecs. And you also mentioned that there were these other. You were looking at different types of dark matter particles using axons. I was just wondering if dark matter were not just made of one type of particle. If you had different species, what kind of effects does that have?
That's a very good question, and people have just started exploring those models. It all depends on whether for the particular model you're thinking about, terrestrial experiments are more tuned to look for those, or if cosmological ones are. So, for example, that additional light species one that I was talking about is saying that, okay, dark matter has at least two components. One is the heavier one, but then there's this non-thermal relic species, which propagates down to redshift 0. And then we are looking for signatures of that. So it will depend from model to model what exactly you should be measuring to look for signatures of it. Okay. I don't know if I quite answered your question. It's an evolving field, so yeah.
Right. But what you said is people are looking into the possibility of multiple.
Yes, so there are people who have thought about dark atoms that, according to them, led to the conclusion that there could be a dark disk, just like the baryonic disk. But that is actually not viable. But there are different models. People have thought about more complicated dark sectors and their impact on structure.
Yeah. It's including, like, say, a fraction of it is action, another fraction of it is something.
Right.
Somebody writes that.
2 participants.
Okay. Which the cursor
is on this page, so let me bring it back.
Sharmari, can you hear me?
You can ask her to. Now she is unmuted.
No, Sharmari seems to be unmuted.
Maybe she cannot hear you unless you speak it to that.
No, but that is all patching.
That's something which is picking you up.
Let me just check whether Shantanu can. Shantanu, can you hear me?
Yeah, I can hear you.
Okay, so Shalvari, maybe there is some issue with your mic. Maybe you can just check. And in the meantime, Shantanu.
Sure.
Acha, Shalvari, hang on. Okay.
Can you hear me?
Yes.
Yes. Go ahead with your question.
I just typed my question. Okay, I was just wondering, what is your starting redshift for your neutrino simulations with neutrinos?
So typically these start at around redshift of 100.
Okay.
So is the question whether they are completely non-relativistic by that?
Yeah, I mean, what is you might lose out information already. Like, do you still use Zeldovich, or do you have to do something special for initialization when you start with neutrinos?
So the gravitational perturbations part is still modeled by Zeldovich, and that seems to be doing fine. The more relevant thing at that redshift is how do you account for the velocity dispersion, and that's what I was trying to say, that depending on your choice for doing that, you can get completely different results. But it is true that for the masses that we consider, they are mostly non-relativistic at redshift 100. In fact, I've checked what happens if you write down the full relativistic equation, and you do not get much of a difference in terms of the predictions at z equal to 0 or z equal to 1.
Okay. Okay. Fine. Thank you.
Santanu, go ahead with your question.
Yeah, so this is just again a general question. So, what are thoughts on the flavor mix dark matter model by Misha Medvedev, where you have quantum mechanical flavor oscillations between the different mass eigenstates? I mean, the neutrino, which is a linear combination of the 4 mass eigenstates. So, I guess among all the dark matter models, this is another model which actually invokes a quantum mechanical property. I mean, similar to the I guess the fuzzy dark matter model. And obviously we have seen flavor oscillations. I mean, this was a 2015 Nobel Prize. So I guess he has shown that it can have effects on large scale structure, but I haven't seen many simulations based on this and invoking baryon. So anyways, this was just a general question.
Yeah, I'm not aware of that particular paper. So if you point me to that, it would be great. And I can try to see what it would take us to actually produce simulations for such a model.
Okay.
Yeah, I mean, a couple of questions. One is, in the neutrino case, we already can calculate the linear power spectrum.
Right.
And for example, with various people, Anand, myself, and Suraj, we have like predicted what happens to the luminosity function of high-redshift galaxies, and said this can be proved at the same time. Your simulation, can you similarly get the mass function of halos?
The halo mass function, yes.
And is it different from putting the velocity spectrum properly and not?
Depending on the mass of the neutrino, yes. If you put it at, say,
what is the mass of the neutrino that you have taken?
So here we took it to be 0.15, the total mass.
Yeah, we had 0.2. We put constraints of 0.2 electrons.
Yeah, so one thing I should point out about the halo mass function is that the change in the halo mass function due to neutrino mass is almost exactly degenerate with a change in sigma 8. Unless you track it as a function of redshift. So we have seen what happens to the halo mass function, but unfortunately, you change the AS, you get the same result.
Right, but we did all the banana that we use this high redshift diamond break galaxy data, not the redshift 0 data. But it's an old paper. Okay, so it is sensitive to the velocity distribution that you
Yes,
take.
yes.
That's a
simple way of asking for people like me. So it appears that when you show that even your physics is correct, suppose if I know what is the velocity dispersion, the way I am going to implement in the simulation is going to change things. For example, if I want to calculate your first implementation, where you just put them as a free-streaming particle starting from that, whatever.
The one that was just noise. Yeah.
So you can predict mass function in such a model. You can predict mass function from some analytical prescription kind of thing. So will they match? Because now I will be confused whether your results are coming from your numerical implementation or real results of this velocity dispersion.
I think 10 years back that question would have been relevant, but now I think we have enough of the good simulations to know what the answer is.
What do you mean by good simulation?
Not just mine, but there are methods developed by other people as well, which have shown that irrespective of which particular method you choose between, say, ABC, you get the same answer, and you get the same answer at the percent level, sub-percent level.
There is another interesting technique which pointed out that the effect of neutrinos on the gravitational potential cannot be very large because the density of neutrinos is very small. So what those people did is to use linear perturbation theory at the Boltzmann equation level to solve for the neutrino effect on the potential, then feed that potential into a full Nbody simulation, and then produce it. So this is an alternate way of doing
this. Is Yasin.
Exactly.
Yeah. Yasin's I wouldn't trust down to fully nonlinear scales because that does some amount of linearization. But recently there was a paper by Elbers and I think Carlos Frank's student, if I'm not mistaken, who has another very interesting method for doing it. And that also produces things correctly deep into the nonlinear regime. So Yasin's method and our method is slightly different if you say.
I guess Anand's question is more about what do you mean by correct? Is it that just because all the techniques are giving the same answer, we believe it is correct, or is there a more?
That's it. So you can do multiple things here. You can see what happens when you include more parts. There are these sanity checks, convergence tests that you have to keep doing to convince yourself that, apart from all the methods converging, what else can you check? Yeah, I fully agree with that. You have to be aware of.
No, the thing which I'm still puzzled by is that everything will depend just on the free streaming length. And then you calculate the linear power spectrum. And you can calculate everything else from there. But what you're saying is that's not correct.
No, that's not correct. Because the neutrinos can also cluster.
Oh.
Depending on their velocity dispersion, if they have very high dispersion, they will only fall into the most massive clusters and nothing else. If they have a lower velocity dispersion, they'll fall into most massive clusters, group-sized objects, etc. Which will change.
Point to electron movements.
Yeah.
The free streaming length is so large.
So the free streaming length, so there are two lengths. One is the free streaming length at which the linear power spectrum starts damping. That is not the same as the gene scale today. The gene scale today is actually much smaller. And there it is possible for you to fall into these.
So what is the gene scale at point to electron?
Today, it's around, I think, 100 megaparsec or something.
Yeah, which is still large, right? Compared to all the.
It is large, but there is a. So the thing with the Fermi-Dirac distribution, the Fermi-Dirac distribution has a low velocity tail. Right. So this average thing that I consider through this genes analysis does not apply to the low velocity tail. The low velocity tail actually clusters quite a bit. You can get over densities of say 20, 30 inside clusters.
Okay, the distribution is like all other.
Can I ask one more question?
Can I ask one question?
Okay.
You have to wait. I suppose.
So this analytical part of the nearest neighbor I find very fascinating. So, because I was trying to do similar things with the Voronoi function. And there I realized that beyond a certain point, at least I was not able to see what can be done analytically. So have you looked at how your nearest neighbors might be able to give generated functions? Something along those lines?
Not quite. What I've looked at is how can we predict these nearest neighbor distributions from, say, spherical collapse, like I was telling you. And it seems like with some sort of bias prescription along with spherical collapse, you get pretty good answers down to, say, 15 megaparsecs or so. But below that, again, it's not clear how you see it. I haven't really thought about it.
It's not clear to me that if you have a distribution in voids, clusters, and all, will you make it out with this nearest neighbor distribution compared to something which has a different topology, like sponge like this thing? And for example, Minkowski functions.
So then, So
or things
the
like
nearest neighbor, the continuum limit of the nearest neighbor distribution is actually Minkowski zero.
Okay, fine.
Yes. But Minkowski higher ones, I'm actually thinking of what the equivalent
is. If you want complementarity or whatever, this thing, then you have to go beyond Minkowski zero.
Right. So I'm actually thinking what it corresponds to in the discrete case.
Okay, so I think it is clear that Arka should visit her very often now. Yes. He is right over the street almost. It is over time and the samosas are waiting for those who are here. I'm sorry to all the Zoom participants who cannot join us for tea. I hope you can come to Ayuka soon and visit us in person. So let's thank Arka once more and
It's a photo by